And then we followed that up with the Generator Statistical Digest, which we published at the start of this year. Now we'll be drawing from that in order to walk through what I'm presenting today, both of those things. So in particular with the GSD 2019, we see in the bottom right, so essentially the GSD provided 2 pages of stats for every DYD or unit in the NEM. The A page basically provided 10 years of history, and in the B page we focus specifically on 2019, and in particular in the bottom right, given the temperatures having more and more impact on generation tech, we presented a graph like this where we looked at local temperature for every dispatch interval in the market and presented how a generator's output and availability suffered as the temperature increased. So I won't name this particular unit, but we can see here from the black line proceeding to the left that as temperature increased, their capability to export to the grid reduced significantly, which is a concern for them, but also for the AEMO and others. Now, in general terms, useful to think about the type of effect that temperature has, because there's a bit of confusion about this. So I'll cut to the chase and tell you the headline result, that essentially most generation technologies are affected in terms of what their peak output capability is. But we can't really find much clear, unambiguous evidence to say that high temperatures make units trip or increase their forced outage rate. So we're happy to discuss this offline if you want. If you think we've missed something, contact me on the feedback email there. But let's go on to discuss the results in more general terms. So for a start, in the NEM, most of the generation plant that boiler-driven steam cycle with steam turbines are coal-fired, but the fuel is immaterial essentially to the technical limitation on the plant. So it could be fired by gas, it could be fired by CST, for instance, or even nuclear. Not that that's likely to enter the NEM for decades to come, if ever. So on the left, what we did was we looked at for every month in the year, we added up the partial unavailability of all 48 coal units that still operate in the market, and looked at how that was trending over time. And essentially, there's a clear increasing amount of partial unavailability, which is due to a couple of different factors. Number one, the AEMO is getting keener and keener on actually making sure they've got the correct data, not just for thermal plant, but for wind farms and solar farms and so on. So reporting's better, but temperatures have actually been increasing over time as well. So there's a clear trend to the fact that when summer rolls around each year, there's more and more limitation on the output of plant like this. In terms of full unavailability, we looked at when the units were offline fully across the year, and conveniently plotted this with summer periods or January periods being the vertical lines, and you can see that they actually coincide with the lowest full unavailability, which sort of makes sense because that's when prices are high and generators do whatever they can to make sure the units are available. But that's a bit inverse to what you might have been hearing elsewhere. Now, also in the GRC, so the generator report card, we basically started the process of looking at some peak output, normalized in this case by registered capacity, right? So 100% output was full output, and looked at what that capability was per degree of local temperature over the period 2016 to 2018, right? And these, what's shown here are 38 black coal-fired units, that were operating up until 2008 and still are. And what we see, mostly the line is pretty flat, right? So you can't see a huge decline. I'd just like to single out two things. The dark green line here is Millmerran, which is an air-cooled station which suffers more at high temperatures than others. And the second, there's actually 4 light blue lines. I think you can see my mouse, that are running across at about 90%, and that's the 4 Liddell units, because they've basically been, for a number of years, they've never run at their full capability because they've been downrated for a number of different technical reasons. So that's the first technology type. If we move on to open cycle gas turbines, there's a SCAD load of them in the market, but the pattern's all very similar, right? So you're not going to be able to read the specific details. I coloured these by region, so red South Australia, for instance, and blues New South Wales, and so on. But there's a consistent pattern where the peak output capability suffers as temperature increases more and more. That's open cycle. Worth highlighting that I have posted before about some confusion that I've seen about the difference between probability and risk, right? So if the probability of a unit tripping in summer doesn't change, the risk of what happens if it does trip can increase because demand's higher and capacity is more used, and most generation technology suffers in the heat and so on and so forth. So when we talk about probability and risk, we need to understand, be clear about what we're talking about. Essentially, there's not, in the data that we've seen, there's not a significantly higher probability of units tripping due to high temperature. Combined cycle gas turbines, the curve is flatter, which makes sense from an engineering point of view, given the technology. So it's flatter than open cycle gas turbines. Again, no significant evidence to suggest that units trip more when it's hot. Reciprocating engines, we didn't actually study in the generator report card specifically, but we did. This is a page from the Generator Statistical Digest, looking at one particular plant that uses reciprocating engines, and we see here that there's a decline in output capability as temperature increases, which again makes sense given the underlying engineering logic. Hydro plant, there's a lot of them in the market, particularly in Tasmania, but some of the key ones were shown here, and it's scant data at the top end, but there doesn't seem to be a huge effect. These ones here, right, where the output drops off, very few half hours or dispatch intervals, where in their locations the temperatures were that high. Wind, right. So again, so this was at the end of 2018. This is a very busy chart. Lots of wind farms in the NEM. Some particular wind farms see quite alarming drops in output capability as temperature goes up. Now, in the GRC, we discussed a few different reasons that this might happen. For instance, it might be that the wind just stops blowing when it's hot in the area of that particular wind farm. It might be that the wind farms were installed more for European conditions without enough cooling on the gearboxes and so on. Or it might be that the wind farms, the networks that the wind farms are connected to locally suffer from heat-related conditions that would constrain the output of the wind farm. At the end of the day, it doesn't really matter from the point of view of delivering power to the grid. It's just something to be aware of. Now, in the process of putting together the generator report card, I singled out a particular DUID, which was actually for Ararat, whose curve showed like this. And after we published the GRC, so June 26th, I published this article, and actually what was of interest to me was in the prior article, I'd essentially created a bit of a competition, which is something we do from time to time, to get people to guess which unit it was, and most of the guesses that came in were that it were something to do with thermal plant. Which to me is just an indication that we need to improve the capability of our thinking in the NEM moving forward. This is data for solar farms up until the end of 2018, which was all the data that we had for the GRC. In the Generator Statistical Digest, again, we've looked at individual results for more solar farms for the whole of 2019, but the pattern's fairly similar. So the straight lines are in the GRC were for units that ran at least a year. And we see that the lines are pretty flat, which sort of surprised me in a way, because from an engineering tech point of view, we know that the capacity of solar PV declines as the temperature gets above about 25 degrees, depends on humidity and a few other factors. But essentially, what we think explains this is that all the proponents who are putting in large solar plant in the NEM are essentially oversizing the PV compared to the inverter size. So behind the inverter, there is actually a decline in capability, but the inverter caps it anyway. So from a market point of view, it doesn't matter. I hope that makes sense. Now, about semi-scheduled availability, so particularly for wind and solar. On the 21st of December, so one of the 4 key events that I noted right at the start that occurred through summer, we noticed, and then the AEMO followed up with the QED for Q4 to note that there was a big decline in output capability that was unforecast. So the image on the right comes from our easy to view software, which basically shows successive AEMO forecasts for aggregate wind output through the afternoon of Friday the 20th of December in Victoria. And we can see that the AEMO had been forecasting that the output would keep climbing through the afternoon and then drop a bit later. What actually happened was the output dropped a whole lot quicker, and that was temperature related. Now that caused a few sweaty palms and furrowed brows and so on in a few different control centres and so on. So what followed then was that the AEMO issued this surprising market notice, or it's surprising to me at least, that basically was almost like a plea that operators of wind and solar farms actually let the AEMO know, as they should, of the high temperature limitations on the output of their plant. So there's two articles that discuss that in more detail, and that's the same day from the AEMO's quarterly QED, quarterly energy dynamics reports that talk about the same thing. So wind output declining as local temperature increased. Just to flag a couple other articles, one of our new software engineers, Marcel Gannon, has a background formerly working with Tilt Renewables and before that in short-term forecasting at the AEMO, and she put this article together, including at the bottom some suggestions for how to make it easier for semi-scheduled operators to actually submit the data that the AEMO is looking for, because it's so the semi-scheduled category has sort of been cobbled onto the market system beginning about 10 years ago, and the way in which data is submitted is not that user friendly. So there's suggestions there for what the AEMO can do, and we're looking at what we could do to help as well. And also there's 2 related reviews that are going on out of the ESB and the AER that have are related to the way semi-scheduled generators operate in the market. In terms of batteries from the GRC, there was scant data, and the dark red line here is HPRG, or Hornsdale Power Reserve. The reason that the output is stuck on 30% there is basically because 30% of its capacity is market enabled, essentially. So that could be considered the peak. There were a few times where its output rose above that, but they're more like aberrations, I guess. So we know that batteries, especially lithium ion, need cooling in high temperature periods. That doesn't so much affect their peak output, it just affects their energy storage capability. So they use up more energy in actually cooling themselves to make sure that they can keep outputting. So that's some of what we've done with batteries. And then for further information, we've got a range of links here. Both the GRC and GSD that we put together last year and the year before, and we'll be looking to update each of those in the new year. So that's all I've got. Peter? Over to Judith.
Sorry, I'm still struggling with my mute button. Thanks very much, Paul.
I was just asking a question because I was in the middle of writing a question. Cool, thank you.
Did you want to go ahead, Peter, or do you want me to?
Yeah, no, I think we can take the questions at the end. If people were happy to do that. Yeah, cool. All
right, now let me just share my screen. So you should be able to see my title slide there, I hope. And this follows on very neatly from Paul's presentation. I'm going to introduce the ESKY project, the Electricity Sector Climate Information Project, which is a collaboration funded by the Department of Agriculture, Water and Environment, managed by the Department of Industry, Science, Energy and Resources, but is a collaboration between CSIRO, AEMO and the Bureau of Meteorology. So I'm going to introduce it very briefly, but then talk about a case study we did. As I said, it follows on directly from Paul's talk, because we're looking at, well, what is the impact under climate change for some of the generation in the NEM. Disclaimer, of course, for any government-funded study. So this case study was an illustration of how to use some of the early outputs of the ESKY study. It's not intended to be conclusive. It's not intended for it to be useful or to be used directly for decision making. The project finishes in a year's time, and all of the underlying data will be available for use by proponents or investment cases or operators. So as I said, a collaboration between Bureau of Meteorology, CSIRO and AEMO, $6 million project over 3 years. $6 million turns out doesn't go all that far in modeling future weather. But to finish, and it was in response to the Finkel review, which acknowledged that the NEM is vulnerable to climate change, and recommended work to look at two things: how you could improve supply and demand modeling under future climates, and so how to make the NEM more resilient under climate change. So that's the goals of the project. The output, so we spent some time in the last year looking, so it's been running, for about 18 months. We spent some time looking at hazards so which variables is the infrastructure vulnerable to? And the emphasis is going to be on, well, how does it change investment decisions? Because if we want to make the grid more resilient, then it has to be a market signal. And if the market signal doesn't work, then of course there are regulatory, this potential regulatory change. I want to be clear that this project is not recommending changes, but what we are testing, and what we're testing in the case study I'm talking about today, is whether the information that we can provide, that we are providing, is actually useful to help differentiate between different solutions. So the output of the project is essentially 3 different kinds of climate information. Time series with high temporal and spatial resolution. So temporal and spatial resolution relevant to the NEM, 30-minute interval data, in some places 1.5 kilometer resolution, in some places more than that, depends on what the climate models are capable of, given the topology and downscaling. So although we're interested in those 4 hazards, temperature, wind, bushfire, which is not a variable but is a compound index, and precipitation, the time series actually do include a full range of climate variables, including wind at ground, 150 meters, 250 meters, humidity, runoff, that sort of information. Those time series then underpin an analysis of high impact weather simulations, so modeling of extreme and compound events. What we found quite early in the project was it's actually fairly straightforward, and the Bureau does this all the time, to produce qualitative simulations, saying we have understanding about how big weather events like cyclones are likely to change, and we can describe it, but that isn't sufficient for investment decisions. So we are doing something which is quite cutting edge, actually globally, which is synthesizing compound weather events, looking in the climate projections to see what some of those extreme and compound events might look like in the future, with the goal of stress testing. And again, based off the time series, and what I will talk more about in detail today is regional thresholds for key climate variables. Paul was really clear that you get pretty abrupt drop-offs as a function of temperature, and there are also other variables like wind on transmission lines that we will be looking at. This is an example of some of the output. So you can see it's from 1980 to 2060. So this is Murray, this is one of the sites we look at. We're modeling at 163 sites around the NEM. So projected temperature range. And you can, as I said, you can see the 30-minute intervals there, and you can see that we're modeling sampled percentiles. This is a single model, but we are doing ensembles of projections so that we can get the range. And you can see there's a very clear temperature trend. It's steady. You could, you know, depending whether it's significant or not depends on the operation of the infrastructure. But temperature is one of the clearest trends in the climate, and some of the others like wind and cyclones or precipitation is way more complicated and regionally complicated. So we are planning to provide that. Here's an example of a projection of an extreme weather event. So on the left, you'll see a historic heat wave, 2009, this is Black Saturday. So January, end of January, early February, that kind of ugly gray, purple gray color is where the temperature exceeded 48 centigrade. And you can see that this is some of our early simulation looking for extreme weather in climate projections. There's one, 2045 is in inverted commas because climate projections is not saying this will happen in 2045. It's saying it is a feasible or plausible event in the next 20 to 30 years. But you can see a couple of things. Not only is it dramatically hotter, but it's dramatically hotter in urban centers. If you look at, for example, the hot conditions up the eastern seaboard and around Western Victoria. So it is, you know, it's an example of what we actually expect to happen. The ESKY project is using a risk framework. It's based on fairly conventional risk frameworks. So ISO 31000, for example, or ISO 14090, which is actually an adaptation risk framework. And what we're focusing on here is the first three steps: understanding vulnerabilities, understanding which decisions are at risk or which models are at risk, and who owns the risk, which is a point that Paul kind of touched on indirectly. Is it the system or is it the proponent? Then understanding the relationship between the vulnerable asset and the climate variables, looking at how that will change in order to quantify the risk. This is in order, as I said, to be able to help stakeholders in the network to test their adaptation options. So, and then of course, after that, the stakeholders themselves have to make the decisions and figure it out. But as I said, we're not recommending outcomes, but we are testing whether the information is sufficient and is in the right form to measure outcomes. So the heat case study, as I'm not going to dwell on this, Paul's covered it very well, but solar and wind farms were identified as vulnerable to temperature. There's a quote down the bottom from the AEMO summer review. So material impacts on wind generation were detected for the first time as a result of temperatures. So they've seen impacts on thermal generation. The relationship with solar power is quite well known, but wind is starting to show a significant vulnerability as well. So I'm going to walk through a relatively straightforward case study. As I said, it's an example of the work that we're doing. We started out with modeling the relationship between solar output and temperature and wind output and temperature. Solar output models are pretty widely available. The curve is that the physics of the panel starts to respond, and then you see the inverters cut out. So quite well known. This is normalized so that it doesn't depend on the size of the wind farm, but can indicate a lot of different wind farms. The wind data comes directly from SCADA data collected by AEMO because, as Paul said, every wind farm operates a little bit differently depending on the engineering specifications. So we use aggregated data from wind farms at 4 different sites just to measure the output. Each of these different colored traces is different temperatures as a function of wind speed along the bottom and the normalized output on the vertical axis. And you can see what you also saw in Paul's data, which is a dramatic drop off once you get over about 40 degrees. The impact of the wind, the impact of temperature on the wind farm is quite dramatic. What we're going to go on to next is an analysis of what may happen in the future. We assumed technology stays the same. We didn't want to add any additional complications, any assumptions about whether they were going to oversize, whether they're going to add inverters to solar farms or change the specifications of wind farms. The other thing that it's based on current technology. It's also, the impact actually includes other weather variables as well, but we found temperature was the most significant. So we did the analysis, as I said, at 4 different locations relevant to renewable energy zones. The models were forecasting output from CCAM, which is a CSIRO conformic cubic analysis model, and it takes multiple global circulation models and then downscales them for Australia. So the global circulation models are very widely accepted. The physics of it has been verified very thoroughly, but they're at very large resolution. So this is the work that's being done by the project, is to make it specific to Australia. So as I said, 30-minute intervals over the next 60 years. So you can we've defined peak periods as between 12 p.m. and 7 p.m. for the 5 hottest days, consistent with AEMO definitions. So what does that mean for the wind farms? As I said, this is a fairly simple analysis. That the plot on the left, the map on the left, is looking at historic temperatures. Sorry, I should have used the same temperature scale as my previous extreme event example, but these two are comparable. And you can see that the projected temperatures are significantly hotter. The yellow-green, the green is over 52 degrees, the yellow is 54 degrees. So if you take a wind farm near Adelaide, which has a historic 10% POE temperature of 44 degrees, that is projected to rise to 46 degrees. So in the next, that's in the next 60 years. And it doesn't mean at the end of the next 60 years either, because there's a lot of variability in the climate projections. So given that, the estimated relationship that I showed earlier, the output on this day would drop from 40% of capacity to 0, given those conditions. Similarly, for a solar farm analysis, this time, if you look, we picked a solar farm near Mildura. So a historic 10% POE temperature of 46 degrees would rise to 48 degrees. And then, so that, given the estimated relationship, would drop off from 70% to 65%. But as you see from the angles on the relationship, that's very sensitive to temperature. It doesn't have to change very much to be significantly more than that. So what is it? Paul had some analysis which looked a little bit like this, so we said, what does that actually look like once you start to get to a greater level of granularity? So this is single day output on a peak temperature day. The blue trace is the wind speed. The black is the wind farm output. And you can see early on the output follows the wind pretty closely. But as the red temperature trace rises, the wind farm drops very abruptly to 0 and stays there for quite a long time during the peak temperature of the day. And so this meant we needed to look at a different, in slightly more detail. So what we have now is a more comprehensive analysis. So this is trends in solar output for the 4 locations that we looked at. If you take the first row, this is the annual mean temperature. The black line is historical, and the blue are projections. The pale blue, so I think this one is was 8 different GCA, different modeling ensembles to give us a perspective. But as I said, the project is working on having a full suite by the end of the project. So the light blue is the envelope. Is what is projected by all of the models. The darker blue gives you the central estimates. So the 25th to 75th percentile range. So, and you can see historically it's a pretty good match. And what it shows for the annual mean is that it's not expected to change a great deal. So this is the normalized solar farm output as a result of temperature. And part of the reason it's not expected to change a great deal is because the irradiance actually is expected to increase slightly to compensate for temperature. So the irradiance will increase because of reduced cloud cover, and the temperature will also rise. And if you look at the peak period means, you see a lot more variability, which is not surprising once you start to get to much more granular data. And you can actually start to see a little bit of a trend, but not significant for solar. On the other hand, here's the wind numbers. So again, annual means for the 4 locations. Wind is not expected to change particularly dramatically. But if you look at wind during peak periods when temperature and of course demand is rising, then there is a pretty steady, if not dramatic, trend in output. So the output's expected to fall quite a bit. So one of the questions that we were testing in this case study was is this data useful? Is it going to result in increased resilience for the grid? So we conducted interviews with renewable energy proponents and with AEMO planners and operations people. And so what we found was, as I said, for wind, there's a negligible change in average output. But during peak temperatures and peak demand periods, which is then the output is already low and highly volatile with a downward trend. So it's worth noting that on peak days, wind output is already lower than average output, and that is expected to decrease significantly. So solar, you see a slight decrease in average output, not really significant, but again, the output during peak temperature, peak demand times is also decreasing. What does it mean in terms of the numbers at the top, by the way, just represent the points on the risk assessment framework. What does that mean in terms of achieving the goals of the project, which is increasing the resilience of the network? So it represents an investment risk, but not a significant one because of the natural economic hedge and because it happens on so few peak days. So it's not likely, what we were told by renewable energy proponents is that it probably doesn't represent a material investment, although the risk could be mitigated. For example, wind farms, more robust specifications for the engineering, for the addition of storage to mitigate against those very fast peak drop-offs. It's a much more significant problem on the reliability side because that severe ramping creates a significant problem for matching supply and demand. And so it is probably an operational problem rather than investment or an infrastructure problem. This can be mitigated in a number of different ways, but will then have to be considered, you know, from a policy, regulatory, and operations point of view. So it's a fairly straightforward case study. We do have a website which has got the early output from the project, including the underlying data that was used for this study. We are proposing up to 5 further case studies, depending on resources and time, and also, to be honest, our partners. So for example, we want to do a transmission case study, but if it looks really bad, we may not be able to publish it, but it will still help us understand whether the data works. So we're looking at doing bushfire, extreme wind, heat on the transmission side, hydro, and then extreme and coincident events. And so that's where we hope we're going. All right, thanks very much, Manishka. I'll hand over to you.
Thank you, Paul and Judith, especially to Paul for highlighting aspects from the generator report and Judith for the ESKY study. We'll move on to the questions now. And as we are moving around, please feel free to write questions on the chat box. Question from Peter, the very first question. This is for Paul, regarding your plots of output efficiency versus temperature, you show the lowering of power output with temperature which you observe. Is there an understanding on humidity impact on different technologies, example gas peaker versus solar?
Thanks, Manisha. So my engineering background is a few decades ago, so I'm a bit scratchy on the details, but yes, humidity does impact on output capability. We haven't actually run numbers to look at the specifics. Just thinking out loud, it would be logical for, if we were going to do something like this, it would be logical for us to just look at use apparent temperature, not air temperature, to do the correlation, and then you'd see the effect of both together. Because essentially for anything that runs on a Carnot cycle, humidity has an impact on the peak output capability. My understanding, I haven't worked in the solar industry specifically, but my understanding is that humidity also impacts on the output capability of PV. What it does to inverters, I don't know.
Thanks, Paul. Another question from Peter. Did I understand correctly that with solar inverter is part of the story of why performance decreases? How does that translate to rooftop PV?
So what we found in looking through the numbers was with the large. So we didn't look at rooftop PV at all. Let's just say for a start, we just looked at large solar farms, and for large solar farms, there wasn't a distinct decline in output at high temperature. And the reason we're pretty sure that this happens is because even though the output capability of DC off the solar PV itself does decline with higher temperatures, what they've essentially done is in effect whacked in 120 megawatts of solar PV and a 100 megawatt inverter. So even if the output of the PV is down to 100 megs at high temperatures, the inverter capped it anyway. So on the grid side, you don't see the impact.
That was for one site, or was that multiple sites?
For all of the ones that we looked at.
Really? All of them had the same problem?
So, well, it's, I wouldn't say it's a problem. I'd say the AEMO can have more assurance that the output capability is going to be there. Like solar has its own challenges, but in terms of high temperature, there wasn't the surprise decline in output that that the AEMO saw through the past summer. If you look at the AEMO numbers, most of the solar farms have higher registered capacity to maximum capacity, which is just basically the DC to AC ratio factor.
Thanks,
Did that
Paul.
answer your question?
Peter, You look happy. Building on to Paul's question earlier, does the data, this is a question from Ahmed, does the data indicate that there is potentially room for solar to inverter capacity modeling to recoup any excess energy?
So thanks for the question, Ahmed. I'm not really sure what it is that you're asking there. So are you able to talk and explain?
Hi. Yeah, absolutely. Hi, everybody. I just wanted to expand on that. You just mentioned, answering Peter's question, that the capacity anyway is higher than the capacity of the inverter.
Yep.
Is that a regular thing or a normally practiced thing in the industry, or is this something that is a requirement?
It's to my knowledge, it's not come out of any generator performance standards or anything like that. It's my guess is that it's come out of the fact that PV is cheap. So it's easier to oversize the solar farm in order to make sure that during winter months, say, where the solar irradiation is not as good, you're still getting a decent output on the plant, so your revenue's higher. So I think it's just a commercial decision to do that, but someone can correct me if I'm wrong.
I'm not an engineer, but what I can do is add what we heard from the proponents, which was that they do see and expect to see that sharp cutoff based on the inverters, but as inverters become cheaper, they expect to just keep adding them, which will reduce the shape of that response.
Okay, so it's just a design thing. It's by design, or so not an issue related to the installation itself.
Not to my knowledge, but if someone knows, or someone knows of someone who knows, can you let me know, and I can update, what we do in the next version of the report.
Okay. Thank you.
Thanks, Ahmed, for the question. Karim has a question. Will or can solar and wind generation technology develop to give better outputs during peak times? Judith, would you like to tackle that question first?
Yeah, sure. And again, this is based on conversations. It wasn't. It's nothing to do with the regulations. So solar, as I've just mentioned, you can improve the inverter performance, or you can improve, the ratio of inverters on solar panels. But there's some underlying physics that can't be changed for solar. Wind generation, it's an engineering question, so it's possible. But what we heard from proponents is it's very expensive. And so that was part of what we were exploring, was that is the impact on investment case sufficient for them to actually start to look at more at the engineering solutions. And, the early answer is probably not, unless it becomes a regulatory requirement. And I don't have an opinion on that.
So can I just add that Judith made the comment that it's a security of supply issue. The fact that over summer, aggregate wind output died very quickly and without prior knowledge of the AEMO. So it didn't so much affect the aggregate revenue over the year of the particular proponents. So their incentive to do something about it is reduced. What I'd say to some extent that might ameliorate that as we go into the future, the NEM's becoming more volatile and will become even more volatile when 5-minute settlement comes in. We've seen in South Australia and even in Queensland in the last, say, 12, 18 months, an increased incidence of negative price. So the incentive for wind farm operators to make sure they're there when the market price is high will increase over time. That might be enough to prompt them to do more in terms of cooling on gearboxes and so on and so forth. But I'm not an investor in a wind farm, so I can't answer fully.
The other thing that I think might be worth adding is that there's no requirement at the moment to take climate change into account in investment cases. And in fact, what they've told us is that investors are not really asking for it yet. So without a regulatory or a policy trigger and without demand from investors, then right now there isn't really a mechanism, because as Paul said, there isn't an economic mechanism. It's just they, if it drops out on a few days when they've got very, very high prices anyway, it doesn't make a big difference to the investment case. What the people who are starting to ask about climate change are the insurers, not the investors.
Thanks. Said is curious to know what would be the potential impact of variations in energy demand and behavioral changes on the system resilience. Judith or Paul?
That is the billion-dollar question. So as our energy inputs become more variable, so energy production becomes more variable, stands to reason that there'll be more and more effort made to shift consumption to when prices are low, away from when prices are high. So, for instance, so through all different mechanisms of a demand response, that makes the challenge of actually knowing what's going to go on a whole lot more difficult. So, for instance, particularly with respect to last summer, January 31st was a doozy of a day where the NEM might have seen its highest ever underlying consumption of demand. So in terms of grid demand, it was a little bit below the peak just before Black Saturday, but in terms of underlying consumption, it was well over that, I think, although there's no official stats on that. The questions are being raised about, for instance, what would happen if we had the same weather pattern next summer at the same time as we're in a COVID-induced work from home environment, and instead of everyone running somewhat efficient air conditioning in CBD office blocks, they're running whatever they've got in so many more distributed locations to keep themselves cool, that it is quite scary in terms of what that would do for supply and demand. Did that answer your question, Saeed, somewhat?
Yeah, I don't have anything to add to that. The system itself, with the as it becomes stringier and as we get more renewable energy, is the resilience of the system as a whole is reduced. But yeah, I agree with Paul. The question of behavior and other random shifts, technology, politics, it's just nobody really quite knows. But the better we can model the part of demand that is related to weather, then at least we can start to take some of that uncertainty out of it.
Thank you. That was a really interesting presentation, and thank you for your answers. Yeah, I think there's a very high uncertainty in the demand changes, but I was just curious to know, do you see this as something favorable? Because on the other hand, people could participate and change their behavior to help the system. Or do you see this as something that could, raise additional issues? Thank you.
So I guess my answer to that would be that the problems are solvable from like a technical engineering point of view. That doesn't guarantee that they will be solved. So it depends on a whole lot of different factors. I guess in terms of what we do, we're trying as much as we can as a private company operating in the market to help people make better decisions so that, we can help collectively to solve those problems.
I just wanted to address Ahmed's point in the chat there as well. Yeah, it is ironic, Ahmed, that resilience of technology, of renewable energy technology, which we hope will combat climate change, is in turn susceptible to climate change. But so are thermal power plants. Every technology of every kind is susceptible to weather in all of its forms. Maybe not every, maybe I'm overstating it. But the better we understand it, then the more we can use it effectively. But there are other technologies like demand management in various kinds, which which actually can help us in these situations.
Thanks, Judith and Paul. We do not have any more questions in the chat. Anybody else, just opening the floor now, anybody else has any immediate questions? Otherwise, we will close off this session.
No one has a question. I'll have one observation from the question. Talked about technology and transmission. I'll just point out AIE has a New South Wales branch, and we had someone talking about transmission constraints, thermal transmission constraints at one of our talks earlier this year. And I think it's online, so if people want to have a look at that, you're welcome to.
Right. Thanks, Peter. So thank you, Paul, and thank you, Judith, for your wonderful presentation, and thank you everyone for participating in this session. And enjoy your lunch and your weekend. Would it be possible to share the slides? Peter is giving a thumbs up, so that's a yes. It will be shared after the presentation. Right. Thanks, everyone.
Thank you.
Yep. See ya.
Thanks, everyone.
Thank you.